All right, so welcome, Kim. Please go ahead.
Thank you so much, David. It's a real treat to get to interact with you guys today. I have to say I would be very happy to be in Florida rather than cold Chicago today, but I guess this is as close as I'm going to get right now. Fred and I are both going to talk with you about some of our recent and not quite so recent work on wetlands, land use legacies, and interactions of wetlands with water quality kinds of issues. And I think we're going to go back and forth a little bit. I will talk, and then Fred will talk, and then we'll come back to me at the end. So I'm going to start with talking about some work that came out actually about 5 years ago, work that I did with Nandita Basu in a paper that we called Signatures of Human Impact. And in this work, we were focusing on an area that I assume many of you are probably pretty familiar with because it's a very important wetland area, and that's the Prairie Pothole region. It's an area of about 700,000 square kilometers, covering the upper Midwest in the US and a lot of area up into Canada as well. And the southernmost area of the Prairie Pothole region down here and over here, you can see comes down into Iowa in what's called the Des Moines Lobe. Now, this is work that was done or begun when Nandita and I were both at Iowa. I'm from Iowa originally. And we got interested in this work not just because of our interest in wetlands and wetland loss in Iowa's Prairie Pothole region, but also because there had been major flooding in the state of Iowa that had led to a lot of work being done thinking about what controls flooding in this area. And as a part of this, this new data set came available that was at the time considered a very high resolution LIDAR data set. So 1 meter LIDAR data. And we thought we could use this LIDAR data set to try to start to understand what did the historical wetland network look like in Iowa. So our objectives in the work were really to better our understanding of the size distribution and the spatial organization of historical wetlands, and then really to explore the role of human impacts in changing these historical patterns, these spatial patterns. Now, what are these human impacts? It's important to remember that in the 1800s, the landscape of Iowa and the Midwest as a whole changed dramatically. Settlers came west. They were plowing up the native prairies there, starting to do row crop agriculture. And in this Prairie Pothole region of Iowa, this was a very wetland dense area. It was a very wet landscape. So farmers came in and they started to dig these trenches like you see over here and to put in pipes, often clay pipes. I love this picture up on the upper right. This is actually a pipe that was recovered from a county in Iowa with a message from the group of people who were putting the pipes in. So tile drainage changed the landscape and made this really the productive agricultural area that it is now, but there was a massive loss of wetland area with this tile drainage that was put in. Today, you see some wetlands remaining in Iowa along the river networks. What you see more frequently is what we call farmed wetlands. And these are wetlands that were either maybe not drained or they were poorly drained originally. So there's still water on the landscape. Farmers often plant them, but crops fail in them more often than not. And just as a fun fact here, this picture here is the land I grew up on in Iowa. There's the Skunk River on the right. I used to go wading there in the summers. And here is a prairie pothole wetland in the field that was at the front of our farm. Okay, let me talk about our methodology in this paper. As I mentioned, we used our LIDAR data And satellite imagery, here's the LiDAR boundary, based boundaries of historical wetlands that we would find. And let's see here, I'm kind of moving my zoom boundaries here. So these are our depressional areas that we identified with the LiDAR data set. And then we would overlay that on Surgo data showing where there were areas of hydric or partially hydric soil. And from overlaying these different data layers, we were able to identify the historical wetland network and then to compare that with the current wetland network. And for current wetlands, we relied on the National Wetlands Inventory wetland layer. And so here we have a comparison of wetland densities based on our constructed historical data set and the current NWI wetlands. And what you can see is, first, a very obvious finding of this work is that overall there was a 90% loss of historical wetland area. And we knew that to begin with. We knew there was a very large loss of wetland area. We also see here, just in looking at the data, that the distances between wetlands also have increased dramatically with this wetland loss. And here we see the distances going from a historical nearest neighbor distance of 150 meters to a current nearest neighbor distance of 197 meters. What else did we see? Well, I told you we were interested in looking at the distribution of wetland size. So here we show that in the historical wetland network, that wetland size followed what we call a power law relationship. So there's orders of magnitude greater numbers of the smaller wetlands than there are larger wetlands here. So here we show, here's our historical wetlands, and the kind of most obvious finding is that there's fewer wetlands now, a very large loss of wetland area, that 90% loss. But next is kind of what we found to be a more interesting finding than that, which is look at the difference in the shapes of these distributions. In the historical wetland network, we saw a more linear power law relationship here. Here we saw kind of a leveling off in the current wetland network. And what does that mean here? Well, what that means is that there appears to be a preferential loss of smaller wetlands. So the wetland size distribution has changed over time. And this can have a number of different effects. One of them is a water quality effect. And I can say simply, smaller wetlands have faster denitrification kinetics, similar to headwater streams. Removing more phosphorus if you're thinking about water quality. And Fred's going to get into that when we move to his portion of the talk. We also know smaller wetlands have higher perimeter to volume ratios. You can get more infiltration of surface water to groundwater from smaller wetlands. So there can be an impact on groundwater recharge and flood control. Next, I say, what about the wetland shape? Has the shapes of these wetlands, have the shapes changed? Now, if you think about perimeter area ratios, just even based on a simple difference between many small wetlands or fewer large wetlands, you have greater perimeter to area ratios if you have a larger group of smaller wetlands. So that's one thing, just in the sheer numbers of wetlands that are there. But you can also have differences in shape. And when you have more complexity in the shape of your wetland, you also have a higher perimeter to area ratio. And let me show you some pictures here. Here is our some images of the historical wetland network superimposed on some satellite imagery of some fields in Iowa. So quite a bit of complexity in those wetland shapes. Now we show you our remaining wetlands on these fields. So we've lost a lot of wetlands, and the wetlands that remained, also the shapes are much simpler. Some of this is just the practicality of farmers trying to work around wetlands remaining in a field. They're taking big equipment around these wetlands. They can't deal with all the complexities, so they'll farm over those areas. So perimeter area ratios are reducing over time, and this can have not only the kind of water quality impacts that I talked about before, but it can have other ecological effects. For example, some studies have shown reduced species abundance with smaller perimeter area ratios. So just to sum up this work, it's kind of cliched, but I would say, you know, we say size matters. Bigger's not necessarily better when you think about wetlands. When you're thinking about the ecological diversity, groundwater recharge, and water quality benefits coming from small wetlands. And I would say really it's not just size that matters, but it's the distribution of sizes that matters. And we need to think about maintaining a distribution of sizes and functionality when you're thinking about protecting and restoring wetlands. And I think this can then segue quite nicely into Fred's next portion, where he really digs into some of the water quality effects of small wetlands. So I'm going to stop my share, Fred, and let you take over for a bit.
Yeah, sounds great. Just let me share my screen. Yeah, so as Kim mentioned here, to ask the questions, well, how much do the small wetlands matter in like regional scale nutrient processing? And really ask the question, why does that matter? So to approach this, in our other paper that we did, we actually conducted a meta-analysis of the nutrient processing rates of different water bodies across the world. So we basically collected data for about like 600 water bodies, like wetlands, reservoirs, and lakes, like all across the world. And we extracted data to try to see if we can see if there's any patterns from these data. So what we extracted from the papers were basically several parameters to calculate how biogeochemically reactive these different water bodies are, this K value, which is basically a rate constant. We were able to represent this through a simple equation that uses the hydrology of the wetland or the water body through the water residence time, as well as the mass balance, the inputs and outputs of that wetland. So basically for a given wetland or wetland size, if you have a higher K value, this reactive rate constant, the more capable it is of removing nutrients such as nitrogen, nitrates, or phosphorus per time. So basically, we plotted this data, and we actually found that when we look at the rate constant versus water residence time, there was a very nice inverse relationship between the two variables. And basically what this means is that these small water bodies are much more capable of removing nutrients like nitrates and phosphates than their larger counterparts. So I don't show this here, but we asked this from the other perspective, basically saying, why does this happen? So we basically produced a mechanistic model and tried to see, can we replicate this really nice inverse relationship that we see in the data? And we did actually indeed were able to replicate this relationship very well. And from that model, we were basically able to tease out why this is happening. So these small wetlands, we found that they actually had a much higher sediment to water ratio, which in essence means that there's a lot more of this reactive interface, this sediment where most of the denitrification happens, where all the anaerobic bacteria live. So because there's a lot more of this sediment, there's a lot more opportunity for the nitrate-laden water to interact with the sediment and be removed and be transformed from nitrate into nitrogen gas. So this kind of leads to the other question. Well, we know small wetlands are more reactive individually, but when we look at a regional scale and we had to ask if we had to remove or restore a certain amount of wetland area, how much does that affect, or how does it affect the regional processing if we took from specifically small wetlands or large wetlands? So in this thought experiment, basically on the x-axis here, we have the amount of area lost in the watershed. On the y-axis, we have the amount of nitrogen removal potential that the landscape is losing based on that corresponding wetland loss. So first we ask, well, if we had to lose 50% of the landscape's wetlands, but specifically from the small wetlands, we actually see that we lose about 80% of the landscape's ability to remove nitrogen, which is, well, a very disproportionate amount of nitrogen that it's processing. So we ask the other question then, if we lose the same amount of wetland area, so that 50%, but starting from the large wetlands, we actually can see that we only lose about 20% of the landscape's ability to remove nitrogen. So these large wetlands aren't playing a large role in regional nutrient processing. So this kind of leads to our next study. So what we did in that paper, in the previous paper, was at a more local scale, and it's using sort of average values for nutrient inputs. So we asked now, can we replicate this at a much larger scale? So the entire US. So how does the entire wet landscape of the US, how is it able to remove nitrogen? But the next interesting thing is that we're able to integrate our data sets to say, at a much finer resolution, how well are the wetlands as well as the nitrogen sources on the landscape, or how well are they co-located in the landscape? So are they actually beside each other so that wetlands can remove the nitrogen in the landscape? And then finally, by combining these two, we can say how much is actually removed. So to do this work, we once again use the National Wetlands Inventory, the NWI. And so for every single wetland in the NWI, we applied the relationships that we found in the previous paper, and by extracting the different attributes of the wetland, so we can predict how much they are able to remove nitrogen based on those existing relationships. So for every single wetland, we can now say what's their fractional end removal potential per wetland. So we remapped those wetlands at a watershed scale, and basically we aggregated and scaled those removal values, potential removal values, to the watershed based on the contributing areas of the wetlands, so we can get those individual values for the watershed. From that, we can now have a map of the fractional wetland nitrogen removal across the US. So we have lots of potential removal of nitrogen, say in what we see in near Lake Superior, where the Prairie Pothole region is, as well as along the southern east coast of the US. And if you're familiar with the wetland density maps of the US, you can see, well, they correspond very well, right? So if there's a lot of wetlands, you can potentially remove a lot of nitrogen. Well, this made sense and just confirms that. But the next step was then to ask, well, how well do these wetlands map out with the actual available nitrogen in the landscape? So this is combining work from our other co-authors, including Danica Burns, where she basically was able to create a nitrogen surplus map or data set across the entire US at the county scale for basically 90 years. So the nitrogen surplus is basically a mass balance at each county where we took account the inputs of nitrogen, so manure, nitrogen fixation, fertilizer, etc., as well as the outputs through crop harvesting. So that net value is the amount of extra nitrogen that can that is in the landscape that can either go into our stream network or can be potentially be intersected by wetlands in that area. So we remapped those county scale values to each of those HUC watershed values. So here we can see, well, where exactly are the hotspots of nitrogen surplus? And obviously in the Midwest, as well as say California, these are areas that have the highest amounts of nitrogen surplus. So combining this data set as well as the previous nitrogen removal data set that we had from the wetlands, we are then able to see how much exactly are we removing through the wet landscape. So this is what we have here. So if you look at this map, you can see that the areas that have the most nitrogen removal are not necessarily areas that have the most wetlands, nor are they areas that have like the highest amounts of nitrogen surplus. It's something in between where you have to have both the sources and the sinks available to have that happen. And through our estimates, we actually found that about 0.86 teragrams of nitrogen are removed by the wet landscape in the US. If you're familiar with the literature, this number is slightly lower than what was predicted before. And we were actually quite worried that we did something wrong. But when we dug into the numbers, we actually found out why this number is a bit lower than usual. And that's because we didn't have this fine resolution data set where we can actually find out with more nuance where the sources and the sinks are. And we explore this in the next couple slides. So from here, we try to categorize the different watersheds in the landscape. So here on the x-axis, we have the wetland density. And on the y-axis, we have the nitrogen surplus. And we basically broke this out into quadrants. So a large plurality of the watersheds are what we call these wetland limited watersheds. So these are areas with fairly low amount of wetlands, but high amounts of nitrogen surplus. So these are areas that have a lot of agriculture, areas that may have historically high amounts of wetlands, but they were drained, as Kim mentioned before. And so these are areas where we really want to look out for. And the other side, we have these areas that are nitrogen surplus limited. So these are the more pristine areas where they have lots of wetlands and fairly low amounts of nitrogen surplus. So these are the areas that we want to, will definitely preserve. We don't want to lose the good amounts of watersheds that we have that are here right now. And then on the third category, we have here the areas that are low input as well as low wetland watersheds. So these are another 40% of the watersheds. These are areas that are probably not historically suitable for wetlands in general, or they are farming. So these are areas that are just low for each category. But the most interesting one is the blue watersheds here, where there actually is that balance between wetland density as well as nitrogen surplus and what we call targeted placement. And why we call this is basically, when we look at the greater scheme of things, we have a lot of watersheds that are in the red area where there is a lot of nitrogen surplus. So when we want to start thinking about restoration and protection, we want to start maybe targeting these red watersheds and start moving them towards that blue zone where we have that more optimal co-location between nitrogen surplus density. And I think Kim will talk about this in our last part of our talk, where we talk about this with a bit more nuance as well. So maybe I'll stop sharing and pass it back to Kim.
Okay, thanks, Fred. Let me see if I can get us situated again here. Okay. So I'm gonna just start up where you left off, Fred, because I think this is a really important set of results here. Because I want to reiterate what we're seeing in the current landscape is just a huge disconnect between where existing wetlands are and where wetlands could make the most difference, which is where those nitrogen surplus values are so high. And of course, makes all the sense in the world that we have this disconnect, because of course, where we're growing a lot of crops and putting a lot of fertilizer on the fields, we've gotten rid of the wetlands. You know, we don't have room for those wetlands because we're trying to intensively grow all of these crops. So we've got a disconnect. And then what Fred's showing here in his slide is that if we start to think about targeted placement of restoration, that's where we could think about making the most difference. So it's with these ideas that we really moved to the next section of our work, where we're more explicitly asking the question, how can wetland restoration contribute to improvements in water quality? And particularly in these kinds of landscapes here, where you've got intensive farming going on. So to move towards this part of the work, we developed another model to do these restoration simulations. And to do that, we first of all went back to what is our fundamental data set, which is our country scale mapping of nitrogen surplus. And I know I saw there's already some questions in the chat about the nitrogen surplus, and I think we can address some of those questions after we finish up here. But to do this portion of the work, we wanted to not work just at the watershed scale, which Fred described in the first portion of the work. We wanted to work at a finer grid scale. And to do that, we went back to the original county scale nitrogen surplus data set from our trend nitrogen data set. And we put that together with the National Land Cover database. And we worked at a 250 meter grid scale, and we used the land use together with these surplus magnitudes to create a 250 meter grid scale map of nitrogen surplus across the country. So here, just going from the lowest magnitudes in the light blue here to the highest surplus values of 70 kilograms per hectare or more in the red areas. Again, you see those very high surplus values in the Corn Belt here, in the Central Valley, and in California, and in other scattered areas across the country. Definitely have some red hot spots in Florida as well. So here we have our input data set here, our grid scale nitrogen data. Next, we go back to the modeling framework that Fred described to you, but with some differences that I will talk us through here. First of all, we're not using National Wetlands Inventory data here. Here we're talking about restoring wetlands. So we're placing new wetlands on the landscape. To do that, we're working at this grid scale here, our grid scale nitrogen surplus data set. So in an individual grid cell, we will start to add wetlands. How do we do that? Well, within the model, we know that we have a size distribution of wetlands, and we randomly select a wetland size from that distribution, and we add that wetland to the grid. So we've got our wetland here. Well, what else do we need to know? We need to know what that wetland is. So we create a wetland catchment area. Well, you might ask, how big is that catchment area? How do we know how big it will be? Well, there's been some great work done recently delineating thousands of wetland catchment areas and areas across the US. So we have a lot of data, and we also have a pretty good understanding of what that distribution of catchment area to wetland area relationship is. So we also use that distribution of values based on data to create a wetland catchment area for the wetland. So next, we think about inputs again. We think, we know what how many kilograms per hectare surplus nitrogen we have in that area. And our assumption here is that that surplus nitrogen is subject to runoff and can pass through the wetland. So there's our surplus nitrogen. That's our input to the wetland. From here, we can go back to these relationships that Fred described between surface area, water residence times, and our nitrogen removal rate constants. So here we can really start to model the nitrogen removal in these scenarios of restored wetland. And again, we're doing this not at the watershed scale, but we're predicting wetland nitrogen removal at the grid scale. So what next? We're not working just at these individual grid scales. We're working across the entire country. So how do we decide where to place the wetlands across the country? And this is where we came up with 3 primary wetland restoration strategies. And the first one is the most straightforward. And in that we say, we're just going to randomly place wetlands across the country. And here I'm showing an example of results for a 10% increase in wetland area across the US. Now, we do have some restraints about where wetlands are placed. We don't place wetlands on developed land, on barren land. They're not placed on shrubland. And of course, we don't put wetlands on top of existing wetlands. So those are our restrictions. And that does create some variability in the wetland density here. Okay, so that's our scenario number 1, random placement. Next, we say, well, let's place wetlands, but let's make sure we're not interfering with agriculture. Let's make sure we're not losing any agricultural area in this scenario. So you can see here a little bit different distribution than with the random distribution. In particular, check out the Corn Belt area here. We've got our lowest densities of proposed restoration wetlands in these areas where we have the most intensive agriculture happening. So that's scenario 2, no agricultural land loss. And then finally, we get back to the idea of targeted restoration. And here, the wetlands are placed where those nitrogen surplus values are the highest. And there you can see, again, we've got a lot of wetlands here in Iowa, other parts of the Midwest, high densities here in the Central Valley. So this is our more targeted strategy here, again, with a 10% increase in wetland area. So the question is, what happens? How much nitrogen removal do we get with this 10% increase in wetland area? So first, I'll just draw your attention to the graph here on the right. We've got 3 different lines. This is our no agricultural land loss scenario down here with the circles, our targeted restoration in the middle, and here's our, oh, I'm sorry, random in the middle, targeted restoration here at the top. So first, you can see that if we're not putting wetlands on agricultural land, it really doesn't matter how many more wetlands we put in the landscape. We're really not getting much of an increase in nitrogen removal. There's just not excess nitrogen there to remove. We get a little bit better results with random placement because we're hitting some of those high nitrogen surplus areas. But by far, we get the most results, the better results with targeted restoration. More wetland nitrogen removal with targeted restoration. And if you look at the actual numbers, here we have the removal rates mapped. Total removal with targeted restoration, we're estimating just over 800 kilotons of nitrogen. Compare that to the no agricultural land loss scenario where we get only 20 kilotons. It's a 40 times greater result by using our targeted approach there. So this, I think, really shows that targeted restoration makes a difference, which is what we were hypothesizing when we began these simulations of restoration. Now, another important question to ask is how much does this all cost? So here's my cost plot. First thing to draw your attention to is, wow, this is expensive, isn't it? We're talking billions of dollars. So yes, it's expensive, but I will say that these dollar amounts that we're predicting here are well within the range of money that we are already spending on trying to improve water quality. They're also within the range of what's been predicted is necessary to meet water quality goals. In the Mississippi River Basin, for example, there was a nice study done, and they estimated, I think, $4.5 billion a year it would cost to get the Mississippi River Basin to its water quality targets of reducing nitrogen by about 60%, nitrogen loading to the Gulf. So this is expensive, but not outside of the realm of numbers that we're used to looking at. Second big takeaway from this plot is, yes, targeted restoration costs a bit more money, but it's a fairly incremental increase here over the no agricultural land loss scenario. And really nothing compared to the difference in nitrogen removal that we're seeing. So yes, targeted restoration is a bit more expensive, but you're getting much more bang for your buck if you're thinking about the water quality impacts here. So I think that is very important. Okay, so there I was talking about country scale results and magnitudes of removal. You can see that they make a big difference, but it's hard to understand what the context of that is. So again, I want to answer the question, what does that really mean for water quality? And to give you that kind of context, I'll focus here on the Mississippi River Basin. So here we all know it's a gigantic watershed. It drains to the Mississippi River, to the Gulf here. Here we have large problems with hypoxia, very large dead zones each year. And we've had goals being set year after year to reduce nitrogen loading to the Gulf, and with very little success. So we first ask, in the Mississippi River Basin right now, with our existing number of wetlands, what difference do those wetlands make? So the modeling there showed us that wetlands in the Mississippi River Basin are currently removing about 440 kilotons of nitrogen each year. To put that in context, that means without those existing wetlands, nitrogen loads in the Mississippi River Basin would be about 50% higher than they are right now. And I think just this absolutely speaks to the importance of, if we do nothing else, at least protecting the wetlands that we got, because they are making a difference, even in their reduced state. So existing wetlands are making a big difference right now. With wetland restoration, however, we could do better. Our results show that a targeted 22% increase in wetland area within the Mississippi River Basin could give us about a 40% reduction in nitrogen loads. And that would certainly bring us closer to our policy goals for improving water quality in the Gulf of Mexico. And here I want to bring the discussion back a little bit to some previous work that we did. With the element model. And I'll say, with our element model, what we've tried to do is to understand what the effects of legacy nitrogen are on water quality. Well, what do I mean by legacy nitrogen? When I say legacy nitrogen, I mean nitrogen that's been applied to the land surface and that remains there. That's nitrogen that doesn't run off in the first year. It accumulates within the landscape over decades of intensive agriculture, where we've got high fertilizer rates, a lot of manure in the watershed. We get legacy nitrogen. Well, what's the effect of that legacy nitrogen? The effect is to drive higher nitrogen loads in the stream, even if we improve our nitrogen management. let's say we reduced our fertilizer application by 50%, by 75%, we might not see nitrogen loads reduce in the stream for years because legacy nitrogen are driving those nitrogen loading trajectories into the future. So in some work that we did within the Mississippi River Basin, we modeled these forward scenarios using our element model. And what we showed is that even with a 100% decrease in the nitrogen surplus, meaning that we're using every bit of nitrogen added to the watershed with 100% efficiency, that even under those very aggressive scenarios, we could reach our water quality goals, but it might take on the order of decades to get to those goals. And, you know, that's a pretty tough message. I've given many talks about this and people hang their heads and say, you are just so depressing. Oh, can't you give us better news? And I think for me, that's what this wetland work is all about. This wetland work is about solutions. And what our work is showing is that with wetland restoration, we can really address these water quality programs. And, you know, a wetland doesn't care if something is new nitrogen or legacy nitrogen. If that nitrogen intersects with the wetland, there's denitrification that can happen there. So I think that's, and I'm going to go back to the other slide, I guess, showing that legacy can have an effect on delaying improvements in water quality, but wetlands really have the potential to help us meet our water quality goals and to jumpstart that process. So I feel very excited about this work and for the kind of heads up that it can give us about the potential for solving these water quality problems. So with that, I'm hoping we have plenty of time for some questions. And I also want to for sure acknowledge our co-authors on these papers. Nandita Basu, of course, who's a professor at the University of Waterloo in Canada. And Danica Burns was also a co-author on the wetland paper, the US wetland paper, and she is a PhD student at the University of Waterloo also. And with that, really happy to answer some questions.
Great, thanks so much, Kim and Fred. If you don't mind stopping your share, we'll bring us big faces back.
Yeah.
And it's pretty incredible. We have lots of questions. I don't know if we'll have time to get through all of them. So I think what I'll do is I'll share a question from the YouTube stream, and then I'll bring it back to the Zoom room. And if you want to ask your question, if you're here live.
Okay.
So, and it's crazy because the question will come on a YouTube stream and then from our audience here. So everyone has got like some confluence going on, which is wonderful. So let's start with the nitrogen budgeting stuff. There were some questions basically about the inputs and outputs, just sort of the logistics of the model. So Blair Buchanan asked if crop harvesting was the only way nitrogen can be removed. And then AJ Reisinger here at UF asked about whether fertilizer and manure inputs are the only ag inputs. What about urban, residential, fertilizer, pet waste? I thought about deposition. So can you just tell us a little bit about any big assumptions you had to make on the end model?
You bet. I've been living and breathing this nitrogen surplus work for a while, along with Danica. So I think I can address some of that. So of course, crop harvesting is not the only way that nitrogen is removed from the landscape, of course. But in our model, that's the only output we consider in terms of calculating what is surplus nitrogen. So there's inputs that go into the landscape. There's nitrogen that's being removed through crop harvest. The balance of that is our surplus nitrogen. Surplus nitrogen then can go a number of different places. We can have denitrification. We can have runoff to the stream. You know, various things can happen. But the crop harvest is kind of the productive pathway that nitrogen surplus is, or the nitrogen flows go out of the landscape. In terms of, so I'm looking at this, so urban inputs. Yes, urban inputs in terms of fertilizer use are included here in our budget. Pet waste is not considered. We've done some work up in the Toronto area where we have taken pet waste into account, and it is significant. We found pet waste around Toronto to be equivalent to atmospheric deposition. So I think in working in urban systems, it's really important to start considering that. I think that was the only question about urban
and then just
systems.
deposition as another source.
Deposition is certainly included, yes.
Okay, thanks, that helps clarify. And Matt, if you're online, if you'd like to unmute, you also had your question mirrored on the YouTube about the quadrants, and if you'd like to ask that question, please go ahead.
Yeah, I think it was, so part of it, great talk, guys. Thank you very much. Obviously, I've read most of this work. I haven't gotten through all of the recent paper, but it was really nice to see you guys sharing the swath of awesome stuff you've done. So yeah, I saw the quadrants that both Fred and Kim you showed. It was, that we divide the world into these categories, but anytime you impose a category, the question comes up, like why? So 10% wetlands is pretty high proportion of a watershed to be wetlands as a delineation, and then the 10 kilogram N per hectare surplus, I think, is also I don't know. I mean, maybe there's a rationale for it, or it was just a convenient way to take a cloud of data and turn it into roughly 4 equal size quadrants. I just wondered if that was meaningful. And I suppose I saw another Joel Tirado Conde sort of had a parallel question on that. And so what's the implication of that? Is it that we should move all of the watersheds to the right? Or is it just that the ones right close to the boundary should be the priorities? Or anyways, I think that there's some sort of dissonance maybe that gets created by something like that.
So thanks for the question, Matt. That's a good question, and it's good to see you. Fred, I think maybe this is something you can address. I know we had a huge amount of conversation about those boundaries and put them in a lot of different places before we ended up with what we got.
Yeah, and like we do acknowledge that it is a gradient, right? So if we had to choose numbers, like for example, for the N surplus one, I think the one that we used was like a mean value of all the watersheds, and that's how we created the boundary. But obviously, like, in the context of like what that means, like we should acknowledge that it's sort of like a gradient. And when we start thinking about like restoration, like it's just areas in this region which can be close or far from that boundary. If wetlands are appropriate there, like that, perhaps that's when we should start moving or start thinking about how far can we move it towards it. Like ideally, well, not ideally, but like there are, we definitely would want more wetlands everywhere, maybe if they're appropriate, but it really depends on like the local conditions. Like, can we put wetlands here, or are there other constraints that allow that?
Yeah, and this brings up a bunch, this actually connects to a number of other questions. So this one came from Dr. Elliott White at University of Virginia asking, is the impact of the targeted restoration driven more by reduction of the highly loaded land or from the end reduction by wetlands? And this question was asked also, like, are the costs of the restoration the only thing included in the cost, or is there the trade-off economic cost of the agricultural production reduction? So these questions about where does the end benefit come from? Is it from removing the land use or removing the N in the wetland? And does the cost include the lost cost of production?
So the benefits that we're seeing here are far and away from the wetland restoration itself, not from the loss of land where you're not applying the nitrogen anymore. I mean, the trade-off is clearly on the wetland. To address the cost issue, we take into account not just the cost of doing a restoration, but we take into account the costs of, it's put in terms of land rental. And the lands that have the highest agricultural productivity have the highest land rental costs. And that's why targeted restoration costs more, because you're taking away land. You have to pay for that land to essentially replace what a farmer would be getting from keeping that land in production.
That makes a lot of sense. Let's see. Let's keep going. If you're a student and you need to run to your next Zoom, that is fine. Otherwise, you're welcome to stay on. Obviously, YouTubers, stick around. I know you're at your desk. There were a couple of questions that came together about, again, coming to this idea of urban settings and stormwater ponds. And this came from Christine. Are you still on? No, she jumped off. So I'll just ask it from, let's see. Stormwater ponds are common and intended to have similar functions as wetlands. How would wetland restoration change if you piped water into, you know, wetlands, like including urban ponds as part of that infrastructure? Is that something you've been thinking about?
So if you piped water into the ponds, you know, essentially turning them into treatment wetlands is, of course, with anything, as Fred was saying, it's all about sources, right? The more source nitrogen that you're adding, in theory, the greater potential for removal.
Would that change your sort of directed, targeted, you know, potentially change some of your targeting if you were considering urban land uses or even just on a small scale as a place for this gain?
Yeah, and I think when you start thinking about targeting in urban areas, I would say this kind of continental scale analysis certainly becomes less useful. As I mentioned, for example, we're not adding wetlands to developed land in this model. I think when you're thinking about urban areas, you've got to start thinking about the smaller scale decision making that happens. But I think you also absolutely have to realize that the inputs can be extremely high in urban areas. The fertilizer rates on residential lawns can be incredibly high. So, you know, these small urban wetlands can make a big difference.
Great, thanks. If there's anyone else on the Zoom that'd like to ask a question live, here's your opportunity.
I have a question. I've wondered this for a while. I mean, the Midwest was a wet place before the tile drainage got going. What would be the consequence of just taking out tiles? Like, forget the wetland restoration, just removing, you know, when the tiles go belly up, or providing incentives to farmers to deal with sort of wetter soil conditions. Do you think that that would have sort of a commensurate nitrogen removal impact that would be maybe more palatable? I don't know. Anyways, just thinking out loud.
I mean, taking out the tiles would be, I don't know, I think you'd have an army on your hands of farmers. I mean, yes, I think there's, you even see denitrification benefits from those wetter, kind of poorly drained areas in the fields, you know, where the tiles aren't working as well as they are. Taking the tiles away would go a long way. I mean, I think you would have issues with maybe not enough organic matter there to really spur a lot of denitrification. But the tiles are the key.
But it might just be a cheaper solution, right? Like, I don't know.
Yeah, or it may, you know, like, you know, I was being a little bit facetious, but the tile removal is wetland restoration in a sense, just like ditch plugs are
right,
wetland restoration.
right.
So it's kind of, you're getting the same biophysical response, shallow water table. Then maybe we'll just end it with one last question. This one also came from Elliot White, and it references the conservation reserve programs and sort of other existing set-asides. And I don't, can you just comment on, like, are they getting 10% of what's needed? Are they able to meet the goals of the load reduction?
So that was one of the things we started looking at when we were developing this scenario. There's specifically a wetland reserve program, and it is an undersubscribed program. You know, there's funds available, and not all of them are taken each year. So I think even with kind of existing allocations, we could do more with wetland restoration. But the amount of funding that is there does not bring us to that 10% level that we were modeling.
Yeah, and it's about location and location and location. So I think that's a really a great take home. And for the students online who are maybe learning about some of these things for the first time, keep your questions. You have any questions when you're writing it up, put them to the side and we can send them to Kim and Fred and maybe get some additional answers.
We would love to hear from you all.
For sure. And we're going to wish Fred best of luck as he approaches graduation sometime in the next calendar year or so. We'll cross our fingers for him. And thank you so much, Kim and Fred, for your talk. We really appreciate you kicking us off this semester. Next week, we have, I'm checking my schedule real quick. We have James Morris, who's going to be talking about the responses of coastal marshes to sea level and strange harmonics in 4D with a twist. It's a symphony. I don't know what we're going to expect, but it sounds like it's going to be awesome for next week. So please be sure to tune in. And thanks everyone. Students, if you have any questions, email us on the Canvas site. Thanks, Kim. Thank you, Fred, so much.
Thanks. Bye-bye.
Have a great day.
Thank you.